multiple x1 through xn is, well, x to the n minus 1, which is the total number of possibilities for the first n minus 1 variables. And then remember, that fixed the prime, and now h of x1 through xn has to be 0 mod p. That fixes boundedly many possibilities for xn mod p. And for a given xn mod p, how many integers between 0 and x can be a given value mod p? Well, the answer is x over p, okay, which is bounded below by x over m, right, bounded above by x over m. Plus 1. You always have to add that plus 1, because even if your range is small, you may still get one root in there. So total number of possibility for x1 through xn is O of x to the n minus 1 times x over m plus 1. That's an upper bound for how many possibilities there can be for x1 through xn. And that's exactly O of x to the n over m plus x to the n minus 1, which is exactly the bound we wanted when k is 2. So that's how we prove the result when k is 2. So that gives a saving. Even k equals 2, this is strictly less than, smaller order than x to the n. Okay, so it's a non-trivial saving. Yeah, right. So actually, yeah, I skipped lots of cases that, yeah. So one couldn't quite do this. One couldn't say G has only boundedly many prime factors if G turned out to be 0. So you have to handle that case separately, right? The number of places where G is 0 is also on the order of x to the n minus 1. You have to show, and there are many little cases like that arise on the way. But that's right. Any other questions? Yeah. That's right. If the polynomials vanished identically, yeah. Right. So h, it's possible that h also vanished at that choice of x1 through xn minus 1. So you have to count how many x1 through x minus 1 would that happen to. So those are little subcases that you sort of have to analyze. But the basic idea is that for most things, G is not going to be 0. That'll determine the prime, and then once the prime is determined, h will not be 0, and then that'll determine xn up to boundedly many possibilities mod p. Okay, so the point is that if you're counting points that reduce mod p to something on a codimension to variety over z mod p for some large prime p bigger than m, then you do have a non-trivial saving. And so how do we handle strong multiples of p squared? Well, we observe that if g of a1 through an is a multiple of p squared for mod p reasons, then if it's for mod p reasons, then if you think about it, both g and its partial with respect to, say, the last variable will have to vanish mod p. Okay, so if g is becoming a multiple of p squared for mod p reasons, if it's mod p reasons, there has to be something codimension 2 mod p going on for just mod p reasons implying being a multiple of p squared. And in fact, explicitly, both g and its partial have to vanish mod p at that point if g is a multiple of p squared for mod p reasons. So you can think about that just by, say, fixing the first n minus 1 variables and just thinking about it as a polynomial in the last variable. You'll see that right away. Say by taking the Taylor expansion with respect to the last variable. See it that way. So, in other words, a1 through an will lie on a fixed codimension 2 variety, mod p. That fixed variety being the variety defined by g and its partial with respect to the last variable. And so we can use the Ekadel type estimate from the previous page to get the saving that we wanted. So what we'd get is that the number of points in a big box of side length x that are multiple, where g takes a multiple of p squared value for some p bigger than m is a strict power saving. Is a strict saving over the total x to the n points box. And that's exactly what you need to do, the square-free sieve, at least for those points where p squared divides g for mod p reasons. So strong multiples can actually be handled totally generally for any polynomial in at least 2 variables. So this argument holds for any multivariable integer polynomial. Nothing special about polynomial discriminants. And that's been very useful for us in handling other polynomials as well. We know that we can dispose of this case right away for any polynomial in at least two variables. So it therefore remains to estimate the number of weak multiples of p squared. In other words, places where f is a multiple of p squared genuinely for mod p squared reasons. And if you look at all the literature in the, it hasn't been phrased this way, but wherever the difficulties come in square-free sieves, this is where they come. It's where things are becoming multiples of p squared really for mod p squared reasons. Okay, so how do we deal with those? In all the polynomials that we've been able to handle, we deal with it as follows. We do some change of variable to transform weak multiples back into strong multiples where the Ekadal-Sieve does apply. So that seems counterintuitive. It's really happening for mod p squared reasons, but often there is a change of variable you can do so that suddenly the weak multiples become strong multiples, and then you can apply the geometric sieve. Okay, so I want to describe how we do this transformation in the case of polynomial discriminants. So the idea is to embed the space of monic polynomials into a bigger space where there are more symmetries, so there are more transformations around, and where we can do this embedding so that polynomials whose discriminant is a multiple of p squared for mod p squared reasons are mapped into points where suddenly it's changed into mod p reasons. So we're taking our space, we're embedding into another space where the mod p squared reasons have suddenly changed to mod p reasons. And I'll show you explicitly how that happens in this case. Okay, but to do this, we first have to understand, okay, because we have to divide it into these two cases, the strong multiples and the weak multiples. Before we know what's happening to the weak multiples, we have to know where they are. So we have to understand how a polynomial can have discriminant a multiple of p squared, first of all, and then when it is a multiple of p squared, when it happens for mod p reasons, and when it happens for mod p squared reasons. Okay, so let's talk about the case where the discriminant is a multiple of p squared for mod p reasons. So in other words, you just care about how the polynomial factors mod p, and that tells you that the polynomial discriminant is a multiple of p squared. So how does that happen? So here's the lemma that tells you exactly when a polynomial has discriminant a multiple of p squared for mod p reasons. Okay, so monic integral polynomial has discriminant a multiple of p squared for mod p reasons if and only if, modulo p, it has a root of multiplicity at least 3, right, or at least 2 multiple roots, right, of multiplicity at least 2. Right, and that's kind of clear from the definition of the discriminant. So remember, the discriminant is the product of the differences of the roots. And so if you're going to get p squared dividing the discriminant, you need some roots mod p to be coming together, if it's only happening for mod p reasons. Okay, so these are the kinds of cases with that the discriminant becomes a multiple of p squared for mod p reasons, and these can be handled, as we said, using this Ekadal-Sieve method. So we don't have to worry about when p squared divides the discriminant for reasons where roots mod p are coming together multiple times, because that lets you on a codimension 2 variety, and it means the geometric sieve. Okay, so now we need to know when can the discriminant become a multiple of p squared for mod p squared reasons. Okay, so there, you're not going to have lots of roots coming together. You're just going to have 2 roots coming together, but they're coming together so much that they're coming together mod p squared. So when is the discriminant multiple of p squared for mod p squared reasons? That's given by this lemma. It says that a monic integral polynomial f of x has discriminant a multiple of p squared for mod p squared reasons, if and only if you can translate the variable by, say, k and z, so that f of x plus k has last coefficient a multiple of p squared, and the second to last coefficient a multiple of p. Okay, so when you write down your polynomial, the very last coefficient will be a multiple of p squared, and the one right before that, coefficient of x, will be a multiple of p. So the polynomial ends with a multiple of p and then a multiple of p squared. And so there you can see that there's only just a double root. It's only a double root. Okay, but because that last coefficient is a multiple of p squared, it causes the discriminant to vanish mod p squared. And you can see explicitly that it's happening for mod p squared reasons. That last coefficient being a multiple of p squared is what's causing the discriminant to become a multiple of p squared. And if you change that p squared to a p, it would only force the discriminant to be a multiple of p. So that's why it's only for mod p squared reasons that the discriminant is being a multiple of p squared in this case. Okay, so those are the weak multiples of p squared. And the question is, how can we lift such polynomials to a bigger space with more symmetries so that the mod